Welcome to this revision workshop on work, energy and power. In this workshop, I am going to look at a past exam question on work, energy and power. And while I do that, as I go through it, I am going to use the question to review certain key concepts in this particular section. Now, this section is often challenging in a NSC paper, and it does not need to be as difficult as sometimes I've seen learners make it, as long as you have a good command of the basic concept. So without further ado, let's take a look at the question. So the question is from the November 2014 NSC paper, and it starts off with question 5. It says, the diagram below shows a track ABC. So we've got ABC. The curved section AB is frictionless. So this part here from A to B is frictionless, but the horizontal section from B to C is rough, which means friction is going to come into play there. So we are dealing with a system where we can apply the principle of conservation of mechanical energy from A to B because there's no friction, so there's no non-conservative forces. Now remember, non-conservative forces are those forces that change the mechanical energy of a system. Now, mechanical energy is the sum of the kinetic and the potential energy, gravitational potential energy. So if you have a non-conservative force like friction, it's actually going to reduce the mechanical energy and hence change it. So it's a non-conservative force because it doesn't conserve mechanical energy. If we were to have an applied force that's consistently pulling the object down, then that too is a non-conservative force. Now that can come in different forms. It could be if you had a little motor here and you had a cable and it was applying a tension force pulling it down, that would be a non-conservative force because it is going to increase the mechanical energy of the object. So it can be a tension, a non-conservative force can be a tension force, can be an applied force directly if someone grabs on it and pulls it down. So when it comes to non-conservative forces, friction is the main one you're going to encounter. An applied force or a tension force, which in essence is basically applied force through a cable or rope. When you have that in the system, you cannot use the law of conservation of mechanical energy, which states that in an isolated system where there's no net external force, the mechanical energy is conserved. Now, from A to B, the only force acting directly on the object is going to be gravity, all right? There is a normal force that is acting, but the normal force acts perpendicular to the direction of motion, so it doesn't affect the motion. There's no work done on the object due to the normal force. We'll come to that just now. The normal force, if there's no coefficient of friction, all right, which is highly idealized, then the normal force doesn't result in a frictional force. Remember, friction acts parallel to the direction of motion, so therefore friction does do work on an object. So it says an object of mass 10 kilograms is released from point A, which is 4 meters above the ground. It slides down the track and comes to rest at point C. So when it says it is released, it means the initial velocity is 0. It's a bit like if I were to drop this, the initial velocity would be 0. Released would mean I let go, and then it goes down the slope. It's not pushed or pulled. So state the principle of conservation of mechanical energy in words. We've done that already. Is mechanical energy conserved as the object slides from A to C? Right, only yes or no. The answer is definitely no, because albeit that it's conserved from A to B, it is not conserved from B to C because there's a frictional force there. So we've answered that. Now it says, using energy principles only, calculate the magnitude of the frictional force exerted on the object as it moves along BC. Now, I want to say this explicitly. From A to B, you may not use the laws, you may not use the equations of motion. Now, the reason for that is that, can you see it's not traveling on a straight line? It's not traveling like this. There's a curve. And the curve results in an acceleration, which is a component of gravity. A equals g sine theta. And as it's doing this, the theta is changing, the sine theta is changing, the acceleration is changing. So it's not rectilinear motion, right? There isn't a constant acceleration. So all your equations of motion, V final equals V initial plus A delta T, V final squared equals V initial squared plus 2A delta X equals V initial plus V final over 2 delta T. And the other one escapes me now. All of them are based on the assumption that the acceleration is constant. The acceleration is not constant here. So the only way we can work with this curved slope is to use energy principles. So let's take a look at this. Now, I would like to quickly talk about the law of work. Let's just firstly talk about work. So if we go, let's just do a bit of revision before I answer the question directly. So a key concept in this section is work. And in my humble opinion, I think that the work concept is the most difficult concept in this section. So I know I myself, as a teacher who had taught work, energy, and power in the IB system, where we used a different approach. It wasn't so focused on work, it was more what I call energy auditing. When I came to NSC, I struggled with this concept. I struggled with it for months until I got my head around the fact that this section of work, this topic, this approach to energy is based on the work done by a force. So if you have a force that is applied on an object, so we have an object here, there's the object, this would be the center of gravity of the object, right? So we have a center of gravity of an object, a force is applied, and there's a change in position. Then work is done. Work is the transfer of energy from the agent to the object. Now remember, when we did specification of forces, this force would actually be specified as force of agent on object. So the agent, for instance, if I now move this like this, I'm the agent applying a force on the object, which is the remote. Energy is transferred from the agent to the object. That energy transfer is work. So the work is done by the agent through a force. So the work done by the force comes from the agent, but it changes the energy of the object. The work done by the force changes the energy of the object. Now, if you look at the formula, and you get this formula on your formula sheet, the work done by the force is the magnitude of the force multiplied by the magnitude of the change of position multiplied by cos theta. Now, I call that cos theta the effective factor. So as the angle gets bigger, cos theta gets less, right? So cos 0 degrees is 1. And then as we go further, I think cos 60 degrees is a half. And then it gets less and less and less. as the angle gets bigger, the cos factor gets less. So if you look here, cos theta times F actually gives you the horizontal component. So if you look here, the horizontal, I actually want to just put it in this color. This is F horizontal, which is F cos theta. So this and this are basically the horizontal component or the parallel component to the change in position. It's the parallel component that's in the direction of the change in position. And the bigger the parallel component is, the more work is done by the agent. Right. Now, anyone who's ever scrummed in rugby knows that if you scrum like this, you're not going to push the opposition very much. But if you go down and you push parallel to the ground, your effect is much more. You're doing more work on your opposition. So the same is true here. If theta is 0 degrees, then your horizontal component is the whole force. As your angle gets bigger, so the effect of your force in doing work, in moving the object, gets less, until at 90 degrees, when the force is perpendicular, the effect is cos 90 is 0 is 0. So this is key. Just because you're applying a force to an object doesn't mean that you're doing work on it. And depending upon the angle at which the force is applied, relative to the direction of the motion, determines how much work is done, how much effective energy, how much energy is actually transferred to the object to move the object. Now, that's the other thing. If you apply a force, but the force doesn't change the position, doesn't move the object, the work done is 0. Because if you don't have change in position, then this is 0. F times 0 is 0. So if I push, and I struggled with this, if I push against this wall and I push until my blood vessels pop, I'm putting effort in, but I'm not doing work, because until the object moves, I'm not doing work. Now that is counterintuitive, because we are programmed to think that work is equivalent to effort. In physics, effort is a force. It's not work. So this is very, very important. Now, as soon as you move an object, the object has mass. If it's got a velocity, it's got a kinetic energy. EK equals a half mv squared. Right? So if now a force is acting, and it's got a net effect, it's going to accelerate and change the velocity. And the change in kinetic energy is the final kinetic energy minus the initial kinetic energy. Half mv final squared minus half mv initial squared. If you take the half times the mass out as a common factor, then you get a half bracket v final squared minus v initial squared. But this does not equal a half m square of the change in velocity, because please don't do this, because this equals a half m v final minus v initial squared, which is a half m, and using FOIL, this becomes v final squared minus 2v final v initial plus v initial squared. And you can see this is definitely not equal to that. So please don't make that mistake. If we're moving an object and changing its position in a gravitational field, then the potential energy is also changing. And the change in potential energy is EP final minus EP initial. So it's MGH final minus MGH initial. Pull the MG out, and you've got MG H final minus H initial, which is MG delta H. Now, this is fine because there's no square. This is not right because there is a square and produces a middle term, mathematically speaking. So be aware of that. Now, question is why have I referred now to changing kinetic energy and changing potential energy? Because remember I said to you that the work done by force changes the energy of the object. What forms of energy? Well, kinetic energy and potential energy. Now, if I'm pushing something horizontally, the change in potential energy is zero because there's no change in height. If I'm pushing something at a constant velocity, there's no change in kinetic energy because there's no change in velocity. So often when we do work, we're changing one kind of energy, but not the other. We might be changing potential energy by lifting it like this, but not the kinetic energy. Or, excuse me, or we could be changing both if I do this, where I'm changing the velocity and I'm changing the height with reference to the ground, for instance. So now, if we come back to the question, I believe that this is your most powerful tool in the work energy power section. You are given this formula. The NC stands for non-conservative. So when work is done by non-conservative forces, it changes the mechanical energy. And that changing the mechanical energy is changing the potential energy plus the kinetic energy sum, which means that you're changing the potential energy and the kinetic energy, and the sum of the two is the change in the mechanical energy. So this is very important. Now, between A and B, if you look at between A and B, if there's no friction, right, then it actually doesn't matter what path follows, because at the end of the day, your kinetic energy and potential energy is going to be the same. Now, that's also not such an easy topic, easy concept. So let's take a general path from A to B, where there are no non-conservative forces. All right? Well, that would mean that on the left-hand side, it's zero. Change in potential energy is potential energy final minus potential energy initial, EPB minus EPA. Changing kinetic energy is EK final minus EK initial, EKB minus EKA. And when I take the two negative terms across, I get EP at A plus EK at A equals EP at B plus EK at B. Hello, I'm getting conservation of mechanical energy. And this is the beauty and the power of this particular formula, that conservation of mechanical energy is a specific case. It collapses from a general case where it takes in the effect of non-conservative forces like friction and tensions and applied forces. But when they aren't there, then the left-hand side becomes zero and collapses to mechanical energy, which is great. So if you're not sure what to use, your foothold, I can't lift my leg high enough, your foothold into a problem, if you're not sure, is that formula. Okay, so let's go back and take a look. It says, using energy principles only, calculate the magnitude of the frictional force exerted on the object as it moves from B to C. Now, I'm going to just take a snapshot of this because I want to take it to another page. Right. So what we're going to do, right, bear with me. Just want to see, yeah. So I just want to see where I want to place it. Okay. I'm going to come back to that. Yeah. So let's go to here. And I'm going to do that for you quickly. So let's take a look. And there we go. Right. So let's go. Using energy principles only, calculate the magnitude of the frictional force exerted on the object as it moves from B to C. So as it's moving here, there is going to be a frictional force. What other forces are acting there? Well, there's the force of gravity, which is the weight. I'm going to rather use Fg because we've got too many W's. We normally use little w for weight and big W for work done. We have the normal reaction, which is acting there. Right, that's great. Okay. But we have no force pulling it forward. It's moving forward because of the fact that it gained energy here, right? And now it's moving forward, but the friction's going to slow it down. There's nothing, there's no little engine in there. There isn't a force pulling it forward. The fact that it's moving forward doesn't necessitate that there be a force in the direction of the motion because of Newton's first law. Right. Now, we are told that it comes to 0 meters per second at the bottom, right? We are told that it is released at the top at 0 meters per second. So it says, using energy principles only, calculate the magnitude of the frictional force exerted on the object as it moves along BC. Now, there are different ways of doing this. You can work with conservation of mechanical energy there, get the velocity at the bottom, then say, okay, now I'm going to work with the changing kinetic energy over here, work out the frictional force. I'm not going to do that. I'm going to use WNC. So here goes. I say, all right, the work done by the non-conservative, and this is really important, forces. If you have more than one non-conservative force in the system, then the sum of the works done by the non-conservative forces needs to be on the left-hand side. Is going to equal the change in potential energy plus the change in kinetic energy. All right? Okay, that's great. Excellent. Right, now, it's important to specify between which points. Now, we do not have the velocity at the bottom there. We could work it out. We could do it. We could use this. We could work it out and then do a second calculation. I'm not going to do that. I want to show you the power of this equation. So I'm going to go from A to B. So watch this. So we're going to do this not from A to B, A to C. So I'm going to do this from A to C, from A to C. All right, agreed? Okey-dokes. All right, so let's see here. Okay, excellente. So it's starting there to there. All right, starting there, ending there. All right, so here goes. So all right. Well, the only non-conservative, and we're doing this from A to B, the only non-conservative force is the work done by friction. There are no other non-conservative forces. There are conservative forces, gravity being it, but that's not included here, is going to equal the change in potential energy. So that's going to be the potential energy at C minus the potential energy at A, plus the kinetic energy at C minus the kinetic energy at A. Why? Because it starts at A and ends at C. The only place where there's friction is between B and C. All right? You say, but Mr. D, what about from A to B? There's no friction. So for the system between A and C, the only place where there is friction is between B and C. And we've been asked to work out that. So let's take a look. So we say, okay, well, EPC is EP final, EKC is EK final, EPA is EP initial, EPC is EP final. We're not working with B. We actually are, but it's happening inside the calculation. That's the power of this equation. I'm a bit like a salesman. I'm trying to sell you the value of the equation. So let's take a look. So what's the work done by friction? Well, if you look at the friction, sorry. Let's go here. The change in position is along here. All right. The change in position is along here. All right. And where the friction acts is over 8 meters between B and C. The friction is not acting between A and B, so we don't have to worry about that. So if we look here, we see, wait a minute. If you look at the block, there's the block. All right, the friction is acting there, and the change in position when the friction is acting is 8 meters. Now, these are not the same type of vectors, okay? There's a very special product that is occurring here, and that's a scalar dot product, which takes two different vectors, multiplies them together to give you a scalar quantity, which in this case is work. So if you take these two and you put them like this, apologies, you put them like this. So I'm just going to redraw this because this might confuse, right? Okay, there's delta x. There's delta x. Delta x is 8 meters. The friction we don't know. The angle between them is always going to be 180 degrees with friction. So friction is always going to have a 180-degree angle between it and the change in position. So when we now work out the work done by the friction, it's going to be the magnitude of the frictional force times the change in position, magnitude-wise. Those absolute values, by now in matric, you should know that that stands for the absolute value, the magnitude, the positive magnitude, or what we know is the modulus, called the modulus. And it's going to be cos 180 degrees, which always equals -1. So the work done by your friction will always be negative. Always, because it takes energy out of the system. It saps the energy of the object and hence slows it down. So that's the left-hand side. The right-hand side, the potential energy at C is mass times gravity times 0. Why 0? Well, we're going to define h equals 0 meters there. And at A, the height at A is going to be 4 meters. Always define your lowest point in the system as having a height of 0. We call that our zero potential. By doing that, your potential energy is 0. Now remember, your potential energy being 0 is relative. If there was a cliff of 1 kilometer here, then you would define your height as 0 there, and then this would be 1 kilometer, and that would be 1,004 meters. Then now this is not your zero potential, this is your zero potential, because now if we pop off here, then it's going to fall and gain a lot of kinetic energy because of potential energy changing into kinetic energy. So you always define your lowest point in the system as your zero potential. Okay, so let's do that. So potential energy at C is 0 minus mass times gravity times the height at A. And this is what I love, is the kinetic energy at C is 0. Why? Because it stopped. Yes, there was a maximum velocity here. There was a maximum kinetic energy here because of gravitational potential energy being converted into kinetic energy. But, because we're working between A and C, the equation takes that into account. So if we look now, we see, well, wait a minute, the kinetic energy at A, drum roll, must also be 0. Why? Because half times mass times 0 squared is 0. And if we look, 0, 0. So your change in kinetic energy is 0. You see, your change in kinetic energy from there to there is in actual fact your change in potential energy. So when we are working with the change in potential energy, we are actually taking into account the change in kinetic energy at B. But now it gets lost from B to C because of the work done by the friction. So it's all in there. It's all in there. So now we can say, okay, so the friction is F, delta X is 8, cos 180 makes this negative, equals negative mass. What did we say the mass was? The mass was 10 kilograms. 10 kilograms times G, which is 9,8. The height at A was, I think it was 4 meters. The height at A was 4 meters. All right. And that's it, because this is all 0. So now we can say, okay, well, the minus signs cancel. And so to work out the friction, we say, okay, this times this divided by 8. So if we do that, right, we've got 10 times 9,8, which is 98, times 4 gives us 392. This gives us 392 divided by the 8, divided by 8 on both sides. This gives us that the frictional force's magnitude is 49 newtons. Fantastic. Fantastic. Can you see the power of this formula? So the best bit of advice I can give you is, if you can, use this. However, sometimes the examiner will limit you as to what you can use. If they were to say to you, you need to solve this using the work-energy theorem. Now, the work-energy theorem, states that the work done by the net force, or the net work done, is equal to the changing kinetic energy of the system. So if you look at using the work net approach, then what you have to do is you have to take every force in the system, work out the work done by that force, and then add them up. Now, I don't like that generally, because quite a lot of your forces are perpendicular to the motion, and so they don't have a contribution. All right? But sometimes they force you to use that. Okay. But using the work net approach, you're basically working with the total work done. So the work done by each of the forces added together, and some of those forces will be negative, some of the work done will be negative, for instance, with friction. Okay. The other option is to use WF net, where you work out the F net, and then you multiply by the change in position and the cos of the angle between the net force and the change in position. So looking here, if your F net and your delta X are in the same direction, it will be cos 0. If your F net and your delta X are in the opposite direction, then it's going to be cos 180. Right, so the work-energy theorem is not my first port of call. I only use it if I'm forced to use it. Because working with the work-energy theorem, you need to work out the net force first. So, if you look at this problem, here, right, if they asked you to work out the net using the work-energy theorem, and I'm not going to do it, I'm going to ask you to do it. What you would need to do is, you could not work out in one calculation W net or WF net, because your F net there and your F net there are very different. And your F net is different here, because if you look on this, if you look here, your mg sine theta is your component down the slope, and I'm busy doing a recording, sorry. Okay, thank you. Your mg sine theta is down the slope, all right? There's no friction, that's fine, but the problem is your theta is going to be changing all the time. And the reason is, if you look at the tangent there, the tangent is changing direction. So you can't work out F net on this slope here. Not with the math you have. So what you would need to do is, you would need to work out, using conservation of energy, what the velocity is here, so that you could work out the changing kinetic energy between B and C. Then here you can work out F net. Here, F net is equal to minus F. Why? Because if your positive direction is to the right, the direction of motion, then your opposite direction is to the left, it's negative. Friction always acts in the opposite direction to motion. So therefore it's negative F. Right, but your change in position, right, is to the right. Now, remember, now you could say, okay, now you could say, well, all right, I could say W net equals, or WF net equals the change in kinetic energy between B and C. Right? So W net would be the magnitude of the friction times the change in position times cos, what did we say? Cos 180. So the left-hand side is exactly the same. Why? Because F net, WF net, is the magnitude of F net, delta x, cos theta, between them. Now, in this case, because F net is negative, it means that F net is acting in that direction and delta x is acting in that direction. So therefore your angle is 180. But what is your F net? Your F net is the negative of the friction. So therefore you land up with F net, the magnitude of F net is the magnitude of the friction force. So you land up with the same thing coming from a different angle. Right, but now let's take a look. What's the change in kinetic energy? This is the change in kinetic energy between B and C. All right, now note that when you're working with the work-energy theorem, the work-energy theorem is the net work done, or the work done by F net is equal to the change in the kinetic energy. We don't work with the potential energy now. The reason is the net force produces an acceleration. The acceleration changes the velocity, and the change in velocity is a change in kinetic energy. All right, so going back here now, what we would find now is here we would have to work out half the mass times Vc squared minus half the mass times Vb squared. That's cool. This is 0. This is 0. But this, we would have to get Vb by doing the calculation using conservation mechanical energy between A and B. You can do that, get the same answer. Personally, I think it's way easier to use the formula that looks more complicated. It looks more complicated, but it's easier to use and it's more powerful. So my suggestion is, if in doubt, use WNC equals delta EP plus delta EK. But when we talk about WNC, we need to be careful. We need to be careful because when we talk about WNC, if I've got a system like this, where I have an applied force to the right, I have a frictional force to the left, and I have a change in position like this, then WNC is going to equal the change in mechanical energy, the change in potential energy, plus the change in kinetic energy. Right? Cool. But now you need to look at the work done by the applied force plus the work done by the frictional force. These two work done by the two non-conservative forces add up to the work done in total by the non-conservative forces. The change in potential energy, let's say it's horizontal, would be 0, and the change in kinetic energy would be plus a half mv final squared minus v initial squared. If this was on a slope, then it would be mg, it would then be mg delta h. But now, the fact that you're adding, you must be careful, because when you add, you're actually subtracting, and this can confuse learners. Let me show you why. This is the magnitude of force applied, delta x magnitude, cos 0 degrees, which equals positive 1. You see, the work done by the applied force is positive. This is going to be positive because it's adding energy to the object, because it's applying a force in the direction of the motion. But WF, the frictional force, is the magnitude of the frictional force, magnitude of delta x, wait for it, cos 180 degrees. Change in position, 180 degrees to the friction force. And this will equal a half mv final squared minus v initial squared. Cos 180 is negative 1, which means this is negative, because friction takes energy out of the object, away from the object. So this is really important. This is something I struggled with for months until I clicked that WNC is not for one force. If there's a system that has two non-conservative forces, it's the sum of the work done by the non-conservative forces. And if there's friction included, then in actual fact, one of those terms is, at least one of those terms, going to be negative. All right. Which in effect lands up being that minus that. But please don't work with the minus. If you work with WF cos delta, WF equals F delta X cos theta, the cos 180 will give you your minus, your negative sign. All right, so ladies and gentlemen, I hope that you have benefited from this, and I will make another video in which I will then discuss power is the rate at which work is done, and we will look at pump problems. Thank you very much, and I will post this, and I sincerely hope that your exams are going to go well. Thank you.